Welcome back to ECE 220. Group A, your lab number 4 is this week. Homework 10, which won't be material on exam 3, is due today. But exam 3 is definitely in a couple of days. That's on Thursday. And before that, the night before Group B, you'll need to turn in your lab number 3 report. After that, things slack up a little bit for Group A people, but Group B students still need to turn in your pre-lab on Saturday. But Friday, we won't have class. We won't have class on Monday either. Today, what I want to do is pick up with RLC circuits, Chapter 8, and we're still yet to force them. We are still just really looking at how they behave after initial conditions have been established. And we've only looked at, so far, the overdamped case, and I thought maybe to get us back thinking about this, let's play a little matching. Now you're given that you have a parallel RLC circuit, and you're given 3 different combinations of parameters, although here the only one that's being varied or changed is the resistor. The inductor and capacitor are always staying at 1 for all 3 scenarios, and these 3 combinations, A, B, C, produce one of those 3 plots, 1, 2, or 3, and what I want you to do is match them up. Does A, that set of parameters with R equal to 1, which of those plots does it belong to? B, those 3 parameter values, again, the only one that's changed is R. It's now 1/2. Does it now match up with 1, 2, or 3? Oh, I forgot. Do you see the 4th plot? None of the above. We'll do a 4. How's that? If we, just in case, we have a none of the above, but now, do you have enough information to make a determination? Can you now connect, can you match A, B, and C, those parameters, with 1, 2, and 3? Take another minute or so to determine how you are going to match those. These are all initial condition responses. You now have a parallel RLC circuit. The initial conditions are the same. You now just let it go under these 3 scenarios, A, B, and C. What I'm going to do, I may have to put some visual aids on, is look at fingers. I'm going to say for parameter set A, do you think it's 1, 2, or 3? And you're going to show me which of those graphs you think it is when I count to 3. And I'm going to then sort of get a collective, well, this is polling day, so we're going to vote. How's that? Today's voting day. We are going to vote for your favorite response. 1, 2, or 3. No red or blue here. Okay, it's just 1, 2, or 3. A. Set A. 1, 2, 3. Wow, I think I have some hanging chads here. Oh, you guys don't even know what I'm talking about, do you? Sorry. So I see some 2s, I see some 3s. I'm not sure which one wins out. I'm going to say that 3 wins out on that one. I don't know, should I indicate that? Okay, B. 1, 2, 3. Okay, I'm doing a very quick polling of that. Now I guess by process of elimination, the majority are but maybe you've changed your mind. 1, 2, 3. All right. So, how can we maybe think about this? Did you write down this equation and then find the roots of that? If you did for each of these, so this one was actually always 1, and all we were changing was this coefficient there. And C was 1. So in this case, in A, we have S squared plus S plus 1. And if you complete the square, I know that's just what you want to do. That's a 3 underneath the radical, the square root of 3. So that the square of the square root of 3 over 2 and the square of 1/2 end up being 1. Where are the roots of that polynomial for parameter set A? Can you tell by the way I factored it? If not, you will by the end of or before exam number 4. You'll know by inspection where the poles are, the roots of that polynomial are, if I give you that factored form. The real part of those roots is at minus 1/2. It's the value of S that causes that first piece to vanish. The imaginary component, or components, we have 2 roots. They're at plus and minus j square root of 3 over 2. These are now roots of S1 and 2 equal to minus 1/2 plus and minus j square root of 3 over 2, which is about 0.86. These are on a unit circle from the origin. 1/2 over and up 0.866. What kind of a response have we described for that set of poles? Or that set of roots? How have we classified? We have overdamped, we have critically damped, and we have underdamped. Do you remember which one goes with which? What goes with these are obviously complex conjugate roots. What kind of behavior do they possess? Overdamped, critically damped, or underdamped? Do we remember? We're talking about this today. This is actually the underdamped case. So set A goes, now do you want to change your vote? All right, what's B? Now I hope see a little bit of the pattern. B is now S squared plus 2S plus 1. This one maybe is easier to factor. so that now S1 and 2 are both at -1. That one we were calling critically damped. And B or C is now S squared plus 4S plus 1. That one, plug into your calculator. The roots are kind of messy. What are they? They are now S equal minus 0.26 with more decimal places or more significant figures. S equal minus 3.73. My screen needs to be bigger. I just made it bigger. Now do we want to revote, or are we happy with our votes from before? We now we do have red and blue and black on the screen. But do you want to say A is still 3? Are you questioning your vote? I'm letting you go back into the polling station and re-vote. Letting you vote twice today. You can re-vote if you want. If you're happy with your first vote, then leave it alone. All right. 1 on A. Is it 1, 2, or 3? 1, 2, 3. Oh boy, people are not wanting to vote the second time, huh? They're done. They want to just forget about it. I don't know what color I am. That's your underdamped response, is number 2. Which one is critically damped versus overdamped? Okay, so that was too mixed up. Which one is overdamped? 1 or 3? Which one has an overdamped response versus a critically damped response? That one's maybe a little more challenging to think about, but in fact, 3 is C. This one is the overdamped, and this one has that nice, sort of nice, I guess. This one is now critically damped. So what color was that? Now, as you are thinking about these different types of behaviors for the same circuit, it just depends on the parameters that you've now connected them with. You could have underdamped, overdamped, or critically damped. Today we're talking about the middle, critically damped, or we'll get to critically damped if we go quick. But when you have, do you see the difference between the 2 and 1 and 3? Do you see a difference between those plots? relative to the shaking that's going on or the oscillation that's going on. Do you see that the middle one actually goes back above its final value? It goes below, then it goes above. The other two do not do that, do they? They go beyond, and then one goes back, and the long tail of 3 and C is due to that really tiny root at minus 0.26. That's causing the tail to be quite long. It has a long time constant. You could find the time constant for those two. It's just the reciprocal of those numbers. This one then is about 4, and this one is 1/3. Meaning, if this was 4, we would have to wait 5 of those, 20 seconds, if my units were correct, for that tail to disappear completely. But this is helping it out, that minus 3 point. It's really collapsing it quickly. All right, those are some of the thoughts I want floating around in your head as we are performing this discussion, or basically derivation, of what's happening with the underdamped response of a parallel RLC circuit. We have this circuit. All of our circuit elements, R, L, and C, are in parallel. And if we derived our differential equation for the inductor current, we would find that it's a second order. Why is it second order? Because it has two derivatives. What's giving rise to those two derivatives? Two energy storage devices, or two energy storage elements in that circuit. Those two energy storage elements are giving us this second order behavior. We could then assume a solution structure of A e to the st, and we will then end up with S needing to satisfy this characteristic equation in the exponent e to the st to give us solution modes for that combination of resistor, inductor, and capacitor. If we select those, and now they're a little different maybe than what I had before. I don't think I used those in the earlier plots, but these will also give rise, because now the L and the R are different. Before I had L equal to 1, C equal to 1, and R was equal to 1. What's going to cause this RLC circuit to be a tank circuit? Do you remember us talking about a tank? What were we doing with the tank? Having water in it and it was sloshing back and forth? How do we keep that water just sloshing back and forth continually? Get rid of that resistor. Get rid of the dissipation. And how do we get rid of the resistor? Take it out. Well, taking that out means what in terms of its value? You just let it go to infinity. So the rest of the circuit sees R as an infinite resistance when you take it out effectively. So now to make the damping less in this circuit, you actually increase the resistance. That's a little counterintuitive. You think, oh, increase the resistance, you're going to increase the damping. But in this parallel RLC circuit, it's just the opposite. You increase R, and the damping now diminishes. So we've now, with all of these combinations of R, L, and C, we've reduced the resistance. We've increased the resistance enough. We've reduced the damping to give us complex conjugate poles. With C equal to 1, L equal to 1/5, R equal to 1/2, we end up with S squared plus 2S plus 5. And again, I completed the square. You're probably going to get tired of, but you did that in algebra, didn't you? Completed the square. What I'm doing is I'm focusing on that coefficient and I'm saying, what when I square it will give rise to that 2 coefficient in the linear spot? So if I squared s plus 1, I would in fact obtain s squared plus 2s. And I then get a 1 squared, and I actually need 5 to be out here. So do you see that I have a 4 left, and this 4 I'm just rewriting as 2 squared. That one was clean in terms of completing the square. And this is our alpha, and this is our damped frequency of oscillation 2. And our roots, if we found them another way, if we went ahead with this formula, which gives us the roots in terms of R, L, and C, we'll get the same result. Here we end up with R of 1/2, or using R of 1/2, L of 1/5, and C of 1, we end up with -1 plus and minus the square root of -4. Or the square root of -1, we play with that a lot as electrical engineers. So we are very comfortable with the square root of -1, and we even give it its own variable name, J, because we deal with I's as well a lot in current. So we have -1 plus and minus J times the square root of 4, which is 2. And I want you to get comfortable making the connection with that and that. The real part, -1, is coming from the s plus 1 factor, and the 2, the omega sub d, the damped frequency, is coming from that omega sub d squared term. Maybe if you don't get comfortable with that, that's okay. The main thing is now we have complex conjugate roots. That's the important thing, which means we now have an underdamped response that we're anticipating. And what we want to do now is derive what that looks like. Before we said, oh, we have one piece of that solution, a e to the s sub 1t. We have another piece, a e to the s sub 2t. Let's distinguish between those a's. And today I thought it would be fun. You may have a different definition of fun, but let's make sure that we at least see, you don't have to rederive this, but you see why we can now assume a little bit different structure immediately once we say, oh, we have complex roots. But right now, let's just start with this. Oh, it's a1 e to the s sub 1t plus a sub 2 e to the s sub 2t. a1 and a2 could be complex. They weren't before in our first overdamped case. We found a1 and a2, and let's now see. Should I do a spoiler alert? Should I just give you the answer? Or should we derive it? Should you anticipate what we're doing? Well, by exam 4, you're actually going to be given a formula sheet. Ooh. Not Thursday. Thursday you don't need this sheet. Okay? But next exam, exam 4, you do. This one is our overdamped. If we have overdamped scenario, we are dealing with that set of equations. If we have underdamped, we have that set. And if we have critically damped, we have that set. And this is getting ahead of the game a little bit because we haven't talked about forcing our systems with step response. We've just looked at natural response, so we aren't dealing with these x's at infinities. Those are the final values of these variables. Ours are all going to 0 in the natural response setting. But we want to now see, how did our a's, a1 and a2, magically turn into b's and cosines and sines with an exponential? Did everyone bring their helmet and have their seat belt? We're going to derive that today. Okay? So hold on. We are now going to figure out why we can just start with what I've circled in red when you now say, oh, I have complex conjugate roots. You now know what alpha is. That's the e to the minus alpha. That's the real part. You know omega sub d. You can plug that in to where the cosine and the sine are. And what you need to find are b1 and b2. And you'll find that from initial conditions. Let's now just, the textbook doesn't even give you this, so I think they cheated you on that one. So let's derive it. They just say, well, it can be shown. Yeah, well, sometimes that frustrates me. So I'm assuming it might frustrate you. Let's now find how the A's here turn into B's. So now I know we're a week late. Halloween was last week, but the costume now is A's are going to be B's. We want to now find A1 and A sub 2. Well, we already know what S1 and S2 are. So let's just plug those in. We have A1, e to the S1. S1, let's say, is minus 1 plus J2 times t. And we're not doing it in general. We're doing it for a specific pole pair, S1 and S2. A sub 2, e to the minus 1 minus J2 t. And now we get to play with our math knowledge. We know that powers in the exponent allow us to factor those terms, or we can now rewrite this as a1 e to the minus t e to the j 2t plus a sub 2 e to the minus t e to the minus j 2t. We've simply rewritten the sum and the exponent as a product of two terms, and that's valid. We now can see that there's a common factor among those two terms on the right. That's the e to the minus t. That's the damping piece. That's what gives us our exponential damping in the underdamped scenario. And it's damping. You can find the time constant. What's the time constant associated with e to the minus t? What value of t causes that exponent? Forget the minus, but what part of t or what value of t causes that to equal 1? It's too easy. T equal to 1 gives us 1, right, for a value. Typically we have e to the minus alpha t. Our time constant is going to be the t that causes alpha t to equal 1, which is 1 over alpha. Here, 1 over alpha, alpha is 1. Our time constant is 1. So in 5 seconds, this underdamped oscillation is going to be exponentially damped. We then have a1 e to the j2t plus a2 e to the minus j2t. And now we rely on Euler. We remember that e to the jx is equal to cosine x plus j sine x. And e to the minus jx changes the sign between the two terms. It's cosine of x minus j sine x. Let's now use that. So this was just sort of an aside. Now we have e to the minus t, a1. We said we needed to change into costume. Now we're going to introduce the cosine and sine. We now have cosine of 2t plus j sine of 2t plus a sub 2 cosine of 2t minus j sine of 2t. Let's now combine the real part and the imaginary parts of this expression, so that now we have e to the minus t. That hasn't changed. We have a1 plus a2 times cosine of 2t. Then we have a plus j times an a1 minus a2 sine of 2t. What were we trying to do? We were trying to find a1 and a2. Let me star this because we may actually use this later, because this is giving us our sine and cosine that we were expecting. And we have the exponential decay, e to the minus t. I usually write it on the front end. Dr. Marcelin, I think, in the formula sheet is using it on the back end, but it's still there. E to the minus t times this bracketed expression. So now we're trying to find a1 and a2. Let's go ahead and go back to our circuit and remind ourselves of what we are dealing with. Let's just suppose that we now have an initial condition on our inductor current. Let's say that's 2 amps. And our capacitor voltage is initially, let's say, 1 volt. And again, this was I sub L of t. And that now allows us to start simplifying, at least trying to find some of these expressions for a1 and a2, or equations for that. Let's now evaluate I sub L t at time 0. That's now going to be, and now I'm evaluating star at time 0. Do you see that the sine piece goes away? Sine of 0 is 0. The imaginary part goes, and we have e to the 0 is 1, and cosine of 0 is 1. That's now just a1 plus a2. And that, we said, let's suppose that's equal to 2. There's one equation that is associated with these unknown coefficients a1 and a2. The next one now is a little bit more interesting. We now need to differentiate that star equation with respect to time to find the time rate of change of I at time 0 plus. Well, let me not do that evaluation just yet. Let me just go ahead and keep it as a function of time. Now, this is one of the reasons we have so many prerequisites for our courses. We have to know how to differentiate. We have to know how to do differential equations, and it takes 3 semesters of calculus before you get into differential equations. So that's where we're at now. We're assuming that background. We differentiate this product of functions as a function of time, and we can say, okay, the derivative of the first, that's minus e to the minus t, times, can I break this? How did I do this? I broke it up into 4 pieces. So now I have a1 plus a2 cosine of 2t plus the first, e to the minus t, times the derivative of the second. What's the derivative of cosine? Minus sine, so I'll change that, and I have to differentiate the argument, 2t, with respect to time. I now have minus 2 sine of 2t. Now I'm going to do the same, but I'm now doing it with the piece that has the square root of minus 1 involved, the j. And I have to keep that j there, but now I have the derivative of the first, which is minus e to the minus t, and here we had let me keep the j, as I said, a1 minus a2 sine of 2t, and then I have finally the first times the derivative of the second, and the derivative of the second is cosine of 2t with a 2. Those are all my pieces parts from differentiating I sub L with respect to time. And what I want to do now is actually evaluate that at t equals 0 plus. And things start to fall out. My sine pieces go away, but I'm still left with a fair amount of terms. I have di sub L of 0 plus dt is now equal to a1 plus a sub 2 with a minus. That's coming from that piece, evaluated at 0. The second term vanishes because it's a sine of 2t. The third piece vanishes because it's also a sine. The last piece gives me some terms. It's now plus 2j a1 minus a sub 2. We okay with those steps? And we can now go back to our circuit. We need to find what is di sub L's value based on our initial conditions. We were given the initial current on our inductor and the initial voltage on our capacitor, we know Eli, that's V sub L of t, is equal to L di sub L of t dt. But everything was in parallel, so in this case, that's the same as our capacitor voltage. And this now gives us a way to solve for di sub L of t is now V sub c of t over L. And if we evaluate that at 0 plus, now we have an expression that utilizes our initial conditions that we were given, the initial value of our voltage on that capacitor. And what was it? 1, and L was 1/5. This gives us now a value of our time rate of change of the inductor current at 0 plus is now 5. The current was 2, and it's changing in a positive way with a slope of 5. Or we can now use this 5 to set minus A1 plus A2 plus 2J A1 minus A2 equal to a value. We now have minus A1 plus A2 plus 2J A1 minus A2 is equal to 5. And that is going to be my second equation. The first equation, if we've forgotten, was A1 plus A2 equaling 2. That was equation 1 from before. And we have an A1 plus an A2 up there. Maybe we can simplify things a little bit. We can now put this in there and maybe clean up the second equation a little bit. We can now say we have minus 2 plus 2J A1 minus A2 is equal to 5, or 2J A1 minus A2 is equal to 7, or A1 minus A2 is now 7 divided by 2J. And that, I'm going to say, you know, that looks a little less involved. Let's call that 2 prime. I'm now going to use 1 and 2 prime to solve for A1 and A2. I had A1 plus A2 equal to 2. And I have A1 minus A2 equal to, should I put the J upstairs? Can I multiply by 1? J over J, so that I now have this is now minus J 7 over 2. I have J squared in the denominator. That gives me minus 1. That minus 1 is now out front, and I have J upstairs scaled by 7 over 2 with the minus sign. I now have these two equations, and A2 is wanting to disappear. If I simply combine those or add those, I now see that I have 2A1 is equal to 2 minus J 7/2. Or I have one equation and the one unknown. I now know that A1 is 1 minus J 7 over 4. I told you, I warned you, these A's could be complex, and they are. That's A1. A2 I can get from Formula 1. A2 is now 1. A1 plus A2 was 2, so I now have 2 minus A1 is A sub 2. This is 2 minus 1 minus J 7 over 4, or A sub 2 now becomes 1 plus J 7 over 4. And do you notice something nice with respect, again, definition of nice, anything interesting between A1 and A2? They're conjugates of each other. Yes. That's usually what happens when you start with real coefficients. We started with real R, L, and C values, and we ended up with coefficients in our answer that are complex conjugates of each other. So that now A1 and A2, or we could just say A1 is equal to A2 conjugate. My definition of nice. Now, where were we? We were trying to find the current going through that inductor, and now we've got complex things floating around, but we had complex exponentials to begin with. If we go back to star somewhere, now we can replace A1 plus A2 and A1 minus A2 in that expression to end up with I sub L. We know what those are now. Those are now determined. We've now determined those. Those are numbers. They're complex numbers, but let's see what happens. Everything else is determined. Now we can say from star, we can say that I sub L of t is e to the minus 2. And what was A1 plus A2? That was right here. That was 1. That was 2. And this one was scaling cosine of 2t. Then we had our next term plus e to the minus t, and this was A1 minus A2 j sine of 2t. And A1 minus A2, A1 was 1 minus j 7 over 4 minus 1 minus j plus j 7 over 4. The real parts cancel. The imaginary pieces come in with a negative sign, and we have 2 of those. So we end up with minus j 7 halves. And this is what's going to go in right there. That's A1 minus A2. So if we replace this with minus j 7 over 2, I now have j squared with a minus. J squared is minus. So I have a minus, that's a plus. And I have a 7 over 2, and the j's are gone. Or I now have my I sub L in a form that I sort of was hoping for. I now have 2 e to the minus t cosine of 2t plus 7 halves e to the minus t sine of 2t. Or you might want to write that as just e to the minus t 2 cosine of 2t plus 3.5 sine of 2t, and that's true for t greater than or equal to 0. What is that? What are we going to call that? We have sines and cosines. Those give us our shaking. And how fast are they shaking? What's their frequency? What's the damped frequency? That was the 2. They're shaking at the same rate. What's the exponential damping? That's the alpha. That's the e to the minus t. So you could draw an e to the minus t from top and bottom to give you this decaying exponential and draw in these sine waves as they collapse, and that's what you have. You have an exponentially damped sinusoid. That's what we will call this, and that's what we had before. What's going to happen at t equal to infinity? What's I sub L of t as t goes to infinity? It better go to 0, right? That's what we expected from the RLC. So if you get all the way done and you go, this is blowing up, must have had some algebra mistake somewhere. None of the above, right? Might want to check your work when that happens, but we could have assumed this, I may get was a B1 and this was a B2, and that's how you'll start from now on. You'll say, you know what? I know it's an exponentially damped sinusoid. I just need to find the B1 and the B2. Forget Tharp's complex algebra stuff. Let me just find the real B1 and B2. And that's what you'll do from this point forward. We'll pick up there with maybe, I don't know, show up and find out. I'll see you tomorrow.